Today we are going to discuss few sections of chapter 13, nuclear reactions. We will focus on nuclear equations, type of radioactivity decay, radiation units, nuclear fission and nuclear fusion. In this picture we can see two of the three units of the Palo Verde nuclear generator station, which is a nuclear power plant and is located in Arizona. The energy generated in this nuclear power plant meets the electrical needs of about 4 million people. But how do the nuclear power plant get the energy? This is one of the questions we will answer in this lecture. But first, we need to know some basic concepts. Let's talk about the nucleus. It consists of protons and neutrons. We know protons, they have positive charge, and neutrons, they are neutral. Because protons, they have the same charge, they repel. Then the question is, how does the nucleus stick together if the protons repel each other? The answer is, there is another force between protons and neutrons that holds the nucleus together. It is the nuclear force or strong force, which is greater than the electrical force. And this force is called a strong force because it's 10 million times stronger than electrical force that hold atoms together in molecules. Another point is the nuclear force or strong force acts in very small distance. If the distance between two protons is greater than 2.5 10 to the power minus 15 meters, then the nuclear force is very weak. This is why the size of the nucleus is of the order of 10 minus 15 meters or 1 femtometer. Now we can answer the question, how do the nuclear power plants get the energy? The nuclear energy is potential energy stored inside the nucleus of an atom. When the nucleus breaks in two or more like nucleus, this energy is released. The energy of one nucleus is a small amount of energy, but the energy generated by billions of nucleus is a significant amount of energy. So the nuclear force plays an essential role in storing energy that is used in nuclear power plants and nuclear weapons. Let's see the relation between atom size and nucleus size. The size of the atom is of the order of 10 to the power minus 10 meters, which is equal to 1 angstrom. The size of the nucleus is between 10 to the power minus 14 and 10 to the power minus 15. The size of the nucleus depends on the number of protons and neutrons in the atom. Then for larger or big atoms, the size will be about 10 to the power minus 14. For small atoms like hydrogen, for example, the size will be about 10 to the power minus 15 meters. Comparing these two numbers, we can see the size of the nucleus is 10,000 times smaller than the size of the atom. It means it's 4 orders of magnitude smaller. Let me explain what order of magnitude means. For example, if the size of the nucleus were 1 meter, then the size of the atom were 10,000 meters. We can see here we had 1, 2, 3, 4 zeros. Then the difference between 1 meter and 10,000 meters is 4 orders of magnitude. The size of the electron is 10 to the power minus 18 meters. It is about 100 million times smaller than the size of the atom. And this is really a small particle. Another good example to get idea about the size of the atom versus the size of the nucleus is the comparison between the stadium and AP. The stadium corresponds to the atom, and the P located in the center of the stadium corresponds to the nucleus. In this scale, the electron will be just a small dot. Now let's talk about the mass of the subparticles of the atom. The mass of the proton is 1.672 10 to the power minus 27 kilograms. The mass of the neutron is 1.675 10 to the power minus 27 kilograms. We can see these two masses are almost the same. But in case of the electron, the mass is 9.109 10 to the power minus 31 kilograms. The mass of the electron is 4 orders of magnitude smaller than the mass of the proton or the neutron. To understand the difference between the magnitude of these masses, we can think if the mass of the electron were 1 kilogram, the mass of the neutron or the proton will be 10,000 kilograms. Then we can see the mass of the electron is not significant compared with the mass of the proton or the neutron. This is why most of the mass of the atom is contained in the nucleus. To study the nuclear reactions, we need to know what is radioactivity. Henri Becquerel, he won a Nobel Prize along with Marie and Pierre Curie for the discovery of radioactivity. Becquerel placed an uranium mineral on a photographic plate, and he found a silhouette of the mineral on the plate when it was developed. Then he concluded that the mineral was emitting an invisible radiation. Today, this invisible radiation is known as radioactivity. Ernest Rutherford later discovered 3 kinds of radioactivity. Now we know there are few more kinds of radioactivity, but in this course we will concentrate in these 3 radioactivities we have in this diagram. The radioactivity phenomenon occurs when an unstable atom releases some particle or energy in order to be more stable. If the nucleus of the atoms emits 2 protons and 2 neutrons, it corresponds to an alpha particle, or the helium nucleus. Also, unstable nucleus can emit energy to be more stable. This energy is called gamma ray. Also, the unstable nucleus can emit a high energy electron, which is called beta particle. All these kinds of radioactivity on nuclear reactions occur because the nucleus is unstable. Also, we say the strong force is the force that holds the nucleus together. There is another force, which is called the weak force, is the mechanism responsible for the nuclear disintegration or nuclear reactions. Let's see what is the difference between chemical reactions and nuclear reactions. In chemical reactions, the nuclei of the atoms from the reactants and the products are unchanged. This is why we have the same element on both sides of the equation. For example, in this case, we had carbon, carbon, we had hydrogen, hydrogen, we had oxygen and oxygen. But in case of the nuclear reactions, the protons and neutrons are rearranged in the nucleus. And this is why they form new elements, because the number of protons and neutrons change during nuclear reaction. In this example, we had iodine in the reactants, but in the products we had different elements. We had xenon plus beta particle. Another concept that I would like to review before discussing each of the nuclear reactions in detail is the isotope concept. Remember the isotopes are atoms on an element that have different number of neutrons. In this example, we had 3 different kinds of isotopes of hydrogen. And we can see the number of neutrons is different in each isotope. However, the number of protons is the same, because if the number of protons change, we will have a different element. Also, we say we can represent the isotope using the nuclear symbol. the bottom number corresponds to the atomic number or the number of protons. This is why in this example we had 1, 1, 1, because it's the number of protons of hydrogen. In the upper part we had the mass number, which corresponds to the addition of the number of protons plus the number of neutrons. And this is why in this case we had 1, because 1 plus 0 is 1. In this case we had 2, because 1 plus 1 is 2. And in this case we had 3, because 1 plus 2 equals to 3. Also, we can represent an isotope if we write the name of the element and then the mass number. Or also we can write the symbol of the element along with the mass number. In this example, we want to find the number of protons and the number of neutrons in the nucleus and the nuclear symbol of the aluminum-25. And first, in order to know the number of protons, we need to know the atomic number. To know the atomic number, we will use the periodic table. Then we can see for aluminum, the atomic number is 13. So the number of protons equals to 13. And first, let's write the number of protons equals to 13. Then we need to find the number of neutrons. We know we can find the number of neutrons if we subtract the mass number minus the number of protons, which equals to 12. Then the number of neutrons is 12. And now the nuclear symbol. To write the nuclear symbol, we write the symbol of the element. In the bottom part, we write the number of protons or the atomic number. And in the upper part, we will write the mass number, which is 25. Then for aluminum-25, the number of protons is 13, the number of neutrons is 12, and this is the nuclear symbol for this isotope of aluminum. Now we are going to discuss each type of radioactive decay in detail. Let's start with the alpha decay. Alpha decay is a radioactive process in which a particle with 2 neutrons and 2 protons is ejected from the nucleus of a radioactive atom. In this example, we had the nucleus of this isotope, of the plutonium isotope. And we can see the nucleus of the plutonium has many protons and many electrons. In order to be stable, then this nucleus ejects 2 protons and 2 neutrons, which correspond to the helium nucleus. And this is why one of the symbols of the alpha particles is the symbol of helium. The 2 in the bottom part correspond to the number of protons, which is 2, and 4 correspond to the mass number, which is the number of protons plus the number of neutrons. This is the nuclear symbol of the alpha particle. Also, alpha particle can be represented for these 2 symbols. One more thing we can notice in this example is when the alpha particle is ejected, the number of protons change in the nucleus. And this is why we had in the products a different isotope. In this case, we had uranium. Let's learn how to write the equation for a alpha decay. In these examples, we had the isotope nucleus of these 2 elements, and this isotope undergoes radioactive decay emitting an alpha particle. Then we want to write the nuclear equation for this nuclear reaction. Let's start with the first example. We had plutonium-240. Let's write first the nuclear symbol for plutonium. Plutonium-240 corresponds to the mass number, then we will write this one on top. To know the atomic number or the number of protons, we will use the periodic table, And in the periodic table, we can see plutonium correspond to, the atomic number for plutonium is 94, so the number of protons is also 94. And now we want to know what is the product if this plutonium emit the alpha particle. We know the alpha particles correspond to 2 protons and 2 neutrons. Then if we write here the number of protons for plutonium, which is 94, then the element in the product has the number of protons will be 94 minus 2, which corresponds to 92. Now let's see what happened with the neutrons. Then first, let's find the number of neutrons for plutonium, which is 240 minus 94. This corresponds to 146. Because plutonium ejects 2 neutrons, then the number of neutrons in the products will be 146 minus 2, which corresponds to 144. And let's see what is the mass number for the isotope or element we had in the products. Then we need to add the number of protons plus the number of neutrons. In this case will be 92 plus 144 will be 236. Then the isotope we will have in the product will be number of protons 92 and the mass number will be 236. We don't know what will be the element here. Plus alpha particle. To know what is the element in the products, then we will use the periodic table. Let's see what is 92 correspond to the uranium. Then in this case, we had uranium in the products. And this corresponds to the nuclear equation for this reaction, for the alpha decay of the plutonium. Let's see the other example. In this case, we had uranium-233. Then the first thing we want to do is to write the nuclear symbol for uranium. And we know the mass number is 233, which is this number. To know the number of protons, we will use the periodic table. Then the number of protons or the atomic number is 92. Then this number goes in the bottom of the symbol. Now let's write the number of protons. The number of protons correspond to 92 in case of uranium, and the number of neutrons will be 233 minus 92, which correspond to 41. And let's see what is the number of protons and the neutrons for the isotope we had in the products. Then the number of protons will be 92 minus 2. Remember, in case of the alpha decay, 2 protons and 2 neutrons are ejected. The number of neutrons will be 141 minus 2, which is 139. If we add the number of protons and neutrons, then we will know the mass number, which corresponds to 229. And now we can write the mass number for the isotope in the products and the atomic number. To know what is the element or what is the isotope in the products, we will use the periodic table. We will check 90 correspond to thorium. And this thorium plus the alpha particle. And this corresponds to the nuclear equation for the alpha decay of uranium, of this isotope of uranium. If we analyze the equations obtained for each these two reactions, we can see in the products the atomic number is reduced by 2 and the mass number is reduced by 4. So we can write a rule in case of the alpha decay. Always in the products the atomic number will be reduced by 2 and the mass number will be reduced by 4. Also, you can see the total number of protons and the total mass number is the same on both sides of the equation. You can see 92 plus 2 equals to 94 and 236 plus 4 equal to 240. And in this case, 90 plus 2 equals to 92, 229 plus 3 equal to 233. Then when you solve the equation, you can just apply the rule. For these two examples, I follow all the procedure because I want you to understand why we can use this rule. Now let's write the nuclear equation for these two isotopes that undergoes radioactive decay. Let's start with the polonium isotope. Then first we will write the nuclear symbol is polonium. The mass number is 208. To know the atomic number, we will use the periodic table, and for polonium is 84. And we'll write here. Now let's apply the rule. Then the mass number will be reduced by 4. Then the mass number of the isotope in the product will be 204. And the atomic number will be reduced by 2. Then will be 82. Plus alpha particle. And let's see what is the element that corresponds to the atomic number equals to 82. And in this case will be lead. And this is the nuclear reaction of the polonium if decay in alpha particle. Now let's see the second example. In this case we had plutonium. And plutonium-242. Let's write first the nuclear symbol. In case the plutonium, the atomic number is 94. Then we write here the atomic number. If the isotope of the plutonium undergoes radioactive decay, then the mass number will be reduced by 4. Then here we have 238, and the atomic number will be reduced by 2. Plus alpha particle we had here in the product. And let's see what is the isotope we had here. Then we need to see for what element has the atomic number 92. And in this case for 92 will be uranium. And in this case there will be the nuclear equation for plutonium. The other nuclear reaction we are going to discuss is the beta emission, and it occurs when a neutron turns into a proton by emitting a high energy electron. Then let's represent this one in an equation. Then we had a neutron neutron is turned into proton plus high energy electron. The high energy electron is called the beta particle. How we can represent this one using the nuclear symbols? And this symbol corresponds to the neutron, and you can see in this case there is no atomic number, or the atomic number is 0 because there is no protons, and the mass number is 1 because we had 1 neutron. In case of the proton, we had 1 in atomic number because we had 1 proton, and the mass number is 1. And this is the symbol for the beta particle or high energy electron. We can see there is no mass number, the mass number is 0, and this -1 just represents the charge of the electron. Then a beta particle is just a high energy electron. In this picture we had an example of the beta emission in case of the iodine. Then iodines emit an beta particle, and 1 neutron is turned into proton, and this is why iodine is converted into the xenon. We can write the equation of the nuclear reaction in this way. Iodine is converted into the xenon plus high energy electron, which correspond to the symbol of the beta particle. Or you can also write the beta particle using this symbol. Either way is correct. And now let's learn how we can write the nuclear equation when a isotope emit a high energy electron. Now let's write the nuclear equation for the beta decay for each of the following isotopes, for iodine and for carbon. Then let's start with the iodine. First we will write the nuclear symbol. To know the number of protons or the atomic number, we will use the periodic table. Then iodine, the atomic number is 53. Then this is the number we need to write here. Then let's write here the number of protons in case of the iodine will be 53. And the number of neutrons will be 131 minus 53, which is 78. If beta decay occurs, 1 neutron will be turned into 1 proton plus high energy electron. Then the isotope in the products, then the number of neutrons of the isotope in the products will be 78 minus 1. Because 1 neutron is turned into proton, but the number of protons will be increased by 1. Yes, then will be 53 plus 1. The total will be 54. Then let's find the mass number. If we add the number of protons or the neutrons, the mass number of the element or the isotope in the product. Then if we add these two numbers, when will we had 131. Then let's write here the isotope in the products. In the product we will have mass number 131 and the atomic number will be 54. And here will we have plus high energy electron or beta particle. Then to know what is the isotope in the products, then just we will use the periodic table, and we know is xenon. Then this is the nuclear equation in this case. Then let's try the second problem. And let's write first the nuclear symbol for carbon. And the mass number is 14. To write the atomic number, we will use the periodic table, and we can see is the atomic number is 6. And this is the number goes in the bottom. That's why here the number of protons for carbon will be 6, and the number of neutrons will be 14 minus 6, which is 8. If beta decay occurs, then 1 neutron is turned into proton plus high energy electron. Then the number of neutrons in the isotope A minus 1 then will be 7, and the number of protons will be 6 plus 1 is 7. And the mass number of the isotope in the product will be 14. And let's write here 14, and the atomic number or the number of protons will be 7. And here will be plus the beta particle. Then to know the isotope we had in the products, then just we will use the periodic table to find the element. Then the atomic number is 7, then correspond to nitrogen. This corresponds to the equation of the nuclear reaction in this case. If we analyze the equations we obtain in these two cases, we can see the mass number in the reactants and in the products is the same. And what happened with the atomic number or the number of protons will be increased by 1. We can see the same happen on this side. The mass number is the same, but the number of protons is increased by 1. And we can apply this rule if we are solving problems related to beta decay. Then in this case, the mass number doesn't change, but the atomic number is increases by 1. Now let's write the nuclear equation for the beta decay of each of the following isotopes, but this time we will apply the rule for beta decay. And let's start with phosphorus. It's 32, and the atomic number for phosphorus is 15, and this number goes there. If beta decays occur, then the isotope in the reactants will have the same mass number, but the number of protons or the atomic number increases by 1, then will be 16 plus beta particle. And now to know what is the isotope we had in the products, then we will see what is a 16 is sulfur. And this is the equation in case of the phosphorus. Let's see for gold. And let's write the nuclear symbol for gold will be, and to know the atomic number we will use the periodic table, which is 79. If beta decays occur, then the mass number of the isotope in the products will be the same, but the atomic number increases by 1, then it will be 80 plus beta particle. And to know what is the isotope we had here, we will use the periodic table, and in this case will be 80. 80 corresponds to mercury. And let's now try to write the equation in case of the sodium. And first we will write the nuclear symbol for sodium, and the atomic number for sodium is 11. If the beta decays occur, then the mass number of the isotope in the product is the same, but the atomic number increases by 1. It will be 12 here. Plus beta particle. And let's see what is the isotope we have here. Then the atomic number 12 corresponds to magnesium. And now this is the equations for each of these isotopes if the beta decay occurs. The other reaction we are going to study is gamma emission, which is high energy electromagnetic radiation from an excited nucleus. To represent a gamma emission, we will use the Greek letter, and in the nuclear symbol, both mass number and atomic numbers are 0, because gamma is just an energy. Since the nucleus changed from excited state to a lower state of energy, there is no change in mass number or atomic number of the isotope. In this example, we can see plutonium is an unexcited nucleus, and when the plutonium releases an high energy electromagnetic radiation, means gamma radiation, then the resultant nucleus is more stable. In the equation, we can represent the excited state of the plutonium using an asterisk, and then to represent the gamma radiation, we will use this symbol, and in the products we will have plutonium with the same mass number and with the same atomic number, but just with lower state of energy. This is why we don't write the asterisk here. A gamma ray is high energy electromagnetic radiation with a very short wavelength and high energy. Now we want to write the nuclear equation for the gamma decay of each of the following isotopes. Then let's start with radon. Then what happened in gamma decay? The excited isotope, in this case of radon. Let's see what is the atomic number for radon is 86. Release an alpha particle, and now the excited isotope will be at a lower state of energy. And in this case, we don't write the asterisk here, but we need to add the symbol for gamma radiation. Let's see in case of the iodine. In case of the iodine, we have the mass number is 125 and the atomic number is 53. Then the excited isotope of iodine release a gamma radiation, and now the isotope of iodine is more stable, and we need to add the gamma radiation. In case of cobalt, the mass number is 60 and the atomic number is 27. This is excited state of cobalt, and to be more stable, the nucleus of cobalt release a gamma particle, and this is why now cobalt is more stable, because release a gamma radiation. Let's see now barium. The mass number is 137 and the atomic number is 56. This is excited state of barium, to be more stable, release a gamma particle, and this is now barium. The isotope of barium is more stable with lower energy, but release a gamma. And these are the equations in case of the gamma decay. In this picture, we had the type of radiation versus penetration. We can see the alpha rays can be stopped using just a paper, but in case of the beta rays, a thin metal sheet is needed. For example, aluminum metal sheet. In case of the gamma rays or X-ray, thick lead or steel plates is needed. For neutron rays, water or concrete is needed. We can see the energy of these rays increase from top to bottom, and most of these rays are dangerous for us. Here we had the summary of the different types of radioactivity decay. First, we had alpha emission, which is identified by the expulsion of helium nucleus or alpha particle. This is why the symbol of the helium nucleus or alpha particles is in the equation. The second one is beta emission and is identified by the expulsion of an electron. And this is why in the nuclear equation we had the symbol for the electron. And the last one is the gamma decay, which identified by the emission of high energy photon. This is why the symbol of the gamma radiation is in the equation. In this picture, we had the electromagnetic spectrum, and we can see the X-ray and gamma rays, they overlap in some part of the spectrum. Remember, the X-ray and gamma rays, they are high energy waves, high frequency waves, but very small wavelength. The question is, if they overlap in some part of the electromagnetic spectrum, how we can distinguish between the two types of radiation? Then the answer is we can distinguish them based on their source. X-rays are emitted by disturbance in the inner shell electrons, but gamma rays are emitted by the atomic nucleus. Then the X-rays is related to the electrons and gamma rays is related to the atomic nucleus. Now we are going to talk about the radioactive decay series. They occur when unstable radioactive nucleus decay. The resultant nucleus may also be unstable. This nucleus continues undergo a series of successive decays until stable configuration is reached. And the unstable nucleus is called the parent nucleus, and the successive decays correspond to the daughter nucleus. There are three naturally occurring radioactive decay series. One is uranium-238 into lead-206. The other one is thorium-238 into lead-208. And the last one is uranium-235 into lead-207. We can see all of them decay into lead, but different isotopes of lead. Let's talk in detail about the uranium-238 to lead-206 radioactive decay series. In this diagram, we had the uranium-238 radioactive decay change. We can see uranium decay in a different isotopes until reached to the stable configuration, which is lead-206. One more thing we can notice is the time for each decay is different. For example, one of them is just minutes, some of them require days, but some of them are really long time. For example, 8.3 10 to the power 4 years. If we add all of these times, then we will get the half-life of uranium. And the half-life of uranium is about 4.47 billion years. And this is why this element is useful in dating the age of Earth. Now let's talk about the nuclear half-life. The nuclear half-life is how long to the nuclear reaction take place. Means how long take for the number of protons and number of neutrons change. In other words, the half-life is the time required for half of the sample to decay. In this graph, we have mass versus time, and we are representing the radioactive decay of a hypothetical isotope with a half-life of 1 day. If the half-life of this sample is 1 day, means after 1 day, the sample will be reduced in half. You can see the initial amount of sample is 1000 grams. Because the half-life is 1 day, after 1 day, the sample will be reduced in half. After another day, this sample will be reduced in half. Then now we have 250. And another 1 day, the sample will be reduced in half. Then the sample decays each day by 1/2 into some other element. The half-life, because it's a time, can be in seconds, minutes, or any unit time up to billions of years. Let's try to solve some problems that involve the half-life concept. If the half-life of hydrogen-3 is 12.3 days, how much time will be required to reduce a 80 grams sample to about 2.5 grams? Then let's write the information we know. We know the half-life equals to 12.3 days. Also, we know the initial mass of the sample of the hydrogen-3 is 80 grams. And we want to know how much time will be required to reduce this sample to about 2.5 grams. Then let's apply the concept of the half-life to calculate that. Then we will start with 80 grams. And then after 12.3 days, the sample will be reduced in half. Then will be at 40 grams. After another 12.3 days, this sample will be reduced in half. Then we will have 20 grams. After 12.3 days, this sample reduced in half will be 10 grams. And then after 12.3, this sample will reduce in half. And we will continue doing the same thing. 2.5 grams. Now we can calculate the time that is required to reduce 80 grams into 2.5 grams for hydrogen-3. Then we had 1, 2, 3, 4, 5. Then the time will be 12.3 days times 5. This equals to 61.5 days. So the time to reduce 8 grams of hydrogen-3 to 2.5 grams is 61.5 days. Let's solve one more problem that involved half-life. In this case, we had the half-life of thallium, which is about 5 minutes. Then we want to know how much time will be required to reduce a 0.5 kilogram sample to about 1 gram. And let's write first the information we had. And in this case, we had thallium 207. And the half-life of the thallium is 5 minutes. And we want to know how much time is required to reduce 0.5 kilogram into 1 gram. And we want to know how much time we will require to reduce 0.5 kilograms into 1 gram. And before to start solving the problem, we can see here the units are not consistent. Then we need to convert 0.5 kilograms into grams to have consistent units. And let's do that first. And we multiply by the conversion factor. Let's cancel out and we will have 500 grams. And what we want to know, what is the time required to reduce 500 grams of thallium to 1 gram. Then now let's apply the half-life concept. Then the initial mass of the thallium is 500 grams. This is the mass of the thallium and it's in grams. Then after 5 minutes, let's right here, this corresponds to the time and is in minutes. This sample will be reduced in half. After 5 minutes, this sample will be reduced in half. And we will continue applying the concept of half-life until we reach to about 1 gram. And now if we divide by 2, there will be about 6.2.5. If we divide this number by 2, we will get 31. Another 5 minutes. Another 5 minutes, we will get 15.62. Another 5 minutes, we'll get 7.81. 5 more minutes, 3.9. 5 more minutes, I'll get 1.5 more minutes, and we will get 0.97, which is about 1 gram. Then now what we need to do is to get the total time, and we will just count 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 9 times 5 minutes, then the total time will be 45 minutes. Now we can write the time required to reduce 500 grams of thallium 207 to about 1 gram is 45 minutes. It is possible to measure the radiation that is emitted by some material, that is received by some material, or that is received by human. To report that measurements, we need to use some units. And now we are going to review some units that are used to report this kind of measurements. For example, the activity of a radioactive source. The units are becquerel in SI system, and is 1 becquerel corresponds to 1 disintegration per second. 1 curie corresponds to 3.7 10 to the power 10 becquerel. To measure the radiation received by a material, the units are gray in SI system, or rad means radiation absorbed dose. And this is the conversion factor between these two units. And to measure the radiation received by humans, we use REM, means Röntgen equivalent man. There is a scale that considers the possible biological damage to humans by certain type of radiation. Usually, the dose we receive is expressed in millirems. If the radiation is in rem, that radiation can be damaged for humans. In this table, we can see different levels of radiation and what are the possible effects for humans. Just before to discuss few of these levels of radiation, remember that 1 rem equals to 1000 millirem. Then if the radiation we receive is 0.130, then this radiation corresponds to the average annual exposure to natural background radiation. Means this is the radiation we receive from phones, from the sun, from the other people. Remember, any material or any body at temperature higher than 0 Kelvin emits some radiation. Then these are the level of radiation that we are exposed each year. And in this case, we had 130 millirems. The upper limit of annual exposure to general public is about 500 millirems. We can see if the radiation is in rem units, then that radiation is dangerous for humans. And we can see here if the radiation is above 500,000 millirems, that radiation is lethal dose for most of the people. Now we are going to discuss two more kinds of nuclear reactions that produce energy. These are the fission and fusion. Nuclear fission occurs in massive nuclei, and they can gain stability by breaking into smaller nuclei with a release of energy. This happens mainly in elements with atomic number greater than 26. In case of the nuclear fusion, this happens mainly in the smaller nuclei, and they can gain stability if they join together with the release of energy. This happens mainly in the elements with atomic number less than 26. Nuclear power plant is a thermal power station in which the source of energy is obtained from nuclear fission reactions that happen in the nuclear reactor. One example of nuclear fusion is the sun. The energy we receive from our sun is produced by nuclear fusion reaction. In some cases, the nuclear fission occurs naturally, but in a nuclear power plant, the fission reaction occurs in the nuclear reactor when a neutron hits an uranium nucleus and makes the uranium nucleus more unstable. And because of that, uranium nucleus splits into two isotopes, in this case krypton and barium, and also release 3 neutrons plus energy. In this case, the uranium is the large atom and the And this arm splits into two smaller ones, which are krypton and barium. This is the equation that represents the fusion reaction, and you can see in the reactants side we had one neutron and the uranium. In the product side we had the krypton isotope, we had the barium isotope plus 3 neutrons. One way we can identify the nuclear fission reaction equation is we will have always one neutron in the reactant side and we will have 3 neutrons in the product side. Also, the isotopes involved in the reaction, they had larger atomic number, as you can see here in case of the uranium, barium, and krypton. In this picture, we can see a nuclear fission chain reaction of uranium, and this is what happened in the nuclear reactor of the nuclear power plants. Remember, in the nuclear fission reaction of uranium, 3 neutrons are generated. These 3 neutrons will start a new fission reaction when hit another uranium nucleus. These 3 neutrons that are generated, another nuclear fission reaction. In this way, the chain of reaction is created. When this chain of reaction is created, then huge amount of energy is released for billions of nucleus of uranium. And this is why in the nuclear power plants, there are mechanisms to control these reactions and avoid any explosion. Now we are going to talk about the nuclear fusion, which is the nuclear reaction that happens in our sun. Nuclear fusion occurs when smaller nuclei they join together in order to gain stability. When they join together, they create a large atom plus energy. We said also the nuclear fusion is the source of energy from the sun and other stars. One of the examples of the nuclear fusion reaction that occurred in our sun is when deuterium reacts with tritium to create helium energy plus neutron. We can see here 2 isotopes of hydrogen, which are small atoms, create helium. Fusion is very desirable source of energy because the supply of deuterium is unlimited, with seawater being a very large source of this isotope. Another advantage is enormous amount of energy is released with no radioactive products. But the problem is the condition in which the nuclear fusion occurs are really complicated. Nuclear fission reaction occur under high pressure and high temperature. When I say high temperature is several thousand of Fahrenheit. Then to meet these conditions is really complicated. This is why up to now there is no any nuclear power plant that produces energy using the nuclear fusion as source of energy. In this slide we had few examples of the fusion reaction equations, and we can see in the reactants and in the products always there are small atoms involved, hydrogen or helium in this case. Then one way we can identify if the equation corresponds to the fusion reaction if the atoms or isotopes that are in the reactants and in the products are small.